Okay, so our final speaker today is Mark Azadpour of AWS, where he's a senior HPC GTM. He's going to talk about AI in development and prototyping for FPGA. He's a specialist for AWS Batch and FPGAs, focused on driving the AWS Batch and FPGA go-to-market strategy and initiatives and advocate usage of containers in HPC. He has worked in the enterprise space for more than 18 years and has extensive ASIC design and verification experience. Sorry. Where exactly are you located, Mark?
Denver, Colorado, in the States.
Okay. Okay. Good morning.
Yes, good morning. Top of the morning to you. Okay, well, thanks so much for that. As I was, mentioned, basically my focus is using FPGAs. So I don't know if everyone is aware of this, but AWS, among other cloud providers, we have instances that includes FPGA. Appropriately, those instance types are called F series for FPGA type instances. And essentially, what I'm going to be talking about is not only we can do design capabilities on cloud, but also prototyping and FPGA enabled emulation on the cloud. So one can go through the whole flow of design from front end to back end simulation as well as emulation on the cloud. And then, the interesting part about the presentation I'm sharing with you today is basically trying to use AI engines to provide functional verification test suite for you. So this is a up and coming and active research, and love to collaborate with anybody who's doing design in this space, such as yourself. So if you're interested, love to follow up after the presentation, and if you can share your RTL, we could basically put it in the AI engine and provide augmented test suite just as a proof of a concept. And also, as we all know, the more we train the engine, the better the results are. So it's really a win-win situation. Now, with that, basically the idea is this. The flow I'm showing right now, it's ASIC flow, but a similar flow applies to FPGA as well. And basically, the problem we are trying to solve today is reducing the verification time that's required in a project, whether it's FPGA or ASIC type final product. In either case, as you can see, I'm sharing some data that was shared by a previous mentor, Graphic, now part of Siemens, which is a ADA provider, if you're not familiar with them. And they do these annual research to see where folks spend their time in a design cycle. And as you can see, this diagram, which was shared by them, a study, commissioned by them, from 2014 through 2020, essentially, the majority of the time is spent in verification, or at least 50%. Now, about 20 to 30% of the folks that participated in studies said, they were doing, somewhere around 25%, and you can look at the different parts of the graph. So the bottom line is we're spending a good chunk of our design cycle on verification. Now, what if we could reduce this, to like 5% or 10%, or maybe 0% if it's fully automated? Then you have 50%, go-to-market speed up by using the tool and flow. So that's what we are, basically aiming, or is the goal of this development is with our partners. So the whole verification cycle essentially starts, basically with getting the requirement and specifications, writing the RTL, running simulations and verification, and measuring the results. And potentially you could have some gate level simulation in the process. And this process itself is iterative. So you continuously go through more verification tasks done, measuring the results, and refining and adding more coverage by adding more tests or quality of the tests that you're running and their regressions being run. So this is basically what we call functional verification or front-end verification. And of course, once we're satisfied with that, which is a subjective matter, I will talk to this on a few slides, it goes to place and route for an FPGA that becomes implementation and mapping. And eventually, of course, in case of an FPGA, once it's burned on the flash, then you're ready to exercise it and basically ship the product. Or in case of an ASIC, then it goes to the ASIC fab, and the product comes back. So then the study looked at, we said about 50 or over 50% of the project time frame is spent in verification. What are the individual tasks within the verification cycle that's being performed by the verification engineers? Now, this is a role definition, right? Verification engineer could be a separate physical person assigned to just doing verification, and or the designer basically playing both roles. So in that case, as you can see, the pie in the left essentially has different phases and different part of the verification. As we can see, 41% is spent in debugging. The next biggest task in terms of time consumption is creating test and running simulation. So the goal of this flow is to basically reduce the 24% to 1 or 2%, and also automate the debugging capability by designing correctly from get-go. So if we had an AI engine that was smart enough and you gave it the requirement in a PDF or markup document, and it could create tests that were meaningful and correct by design, then the verification process could shrink, as you can see, by 60-some%. Now, granted, you cannot take both of these two tasks to zero, so even a 50% goal that we have set is a lofty goal, and it's a huge improvement in the whole design verification cycle of FPGAs and ASICs. Again, this is a chart. This one specifically was commissioned for FPGA folks, so that really applies here. So again, same paradigm applies. More than 50% of time of a project is consumed during the verification cycle. And the interesting observation in here is when you talk or when the FPGA verification folks were questioned, they rated the time spent among the full project to be 70%. So that means that basically verification folks think that the duration of verification is even then larger than what it really is. So that tells you the pain point of the verification process and that sequential iterative type of the process we go through. So again, the problem we're solving is, trying to reduce that. And also, there was another study done, or a chart in this study, that showed folks have tried to mitigate this long pole in the process by throwing more human or resources to it. So the study looked at the number or the ratio of verification versus design, and basically, sorry, this is incorrect. So for every 2 designers, there was 1 verification engineer on average in 2014, and now it's pretty much 1-to-1 when the study was done. So that's saying that basically the management and project management is well aware of the issues and the long pole and trying to resolve the problem by increasing the resources allocated to verification. Of course, there is a limit to how much you can improve by assigning more folks to verification versus design, because as we looked at it, verification is a sequential and reiterative process. You design a test suite, you run it, analyze it, and back to step 1. So no matter how many resources one assigns to this, still it's time consuming. So really that's that's the motivation, and basically that is the statement of the problem. And finally, this is a very interesting note. What percentage of projects are completed on schedule or on time? As we can see, basically, the trend is pretty much consistent. So, typical optimistic view that we always plan for the best case, and typically because of that debug and coverage closure and or other processes such as implementation and so on, somewhere around 65+% of the time the project completes behind schedule. So that's an interesting observation. So with that, again, looking at another statistics, basically, what are the causes of respinning in ASIC, which doesn't apply to FPGA, but regardless, we can see the functional verification and bugs in the design are the majority culprit of the issues, as this chart alludes to, which again, the gating item for that is having a good quality functional verification suite and ability to run those or run regressions faster. So both of those issues can be resolved if we had a more intelligent test suite that was generated and was correct by design from the specification. And that is the task we're trying to address. So basically, what I'm trying to show in this slide is that, this is the flow we are running today. So basically, say if you have a PCIe 3 test suite that was created manually, we can take that and also PDF definition of PCIe 4, if that's what we're trying to verify now, and feed that to our, AI ML engine. And underneath, of course, we're running GPUs from NVIDIA, and a similar library to what Cosmos is, and that's for robotic automation. But a similar engine is in development to basically run it through the RTL and generate the Delta test suite. So notice we are not taking designs from scratch, because the whole point is we want to accelerate first the new versions to train the the ML engine, and eventually we want to go to the case where we eliminate the whole having a test suite generated manually and have the engine run it. And mind you, different designs we all know, some of them are, say, memory hungry, the other one are CPU intensive, and depending on the specs, there are different fine tuning that needs to go into the model generation. So those models need to be tuned per industry and per use case of the type of chip or family of chips we are trying to validate. Now, once that data is generated, we have an orchestrator, which is called Batch Orchestrator, which I am the BDM for within the cloud. Similar to LSF, if you are familiar with that, and that can orchestrate running the simulation on F instances. So right now we are in second generation F or FPGA instances at AWS, so it's called F2 instances. So then you have a farm of FPGAs that we basically burn the design or download the design into the FPGA for the sake of running, 20 times or however many times faster than a pure simulation. So this flow allows you to basically take full advantage of AI ML capability as well as execution speed up. Notice those were the two items that were identified in functional verification as being the bottleneck. So this flow trying to solve that. And we can do this today fully in cloud. So you take all the advantages of using FPGA on the cloud. So you don't need to have the infrastructure, the board, the hardware, and you can basically do functional verification from anywhere. So you log into the cloud from your home or wherever, and you launch the process. So basically, this is a little bit double clicking on what an F2 instance does. So basically, there's an entity called Amazon Machine Image or AMI. And what that does is basically defines a container that is needed to resurrect an instance. And what that does is once you say, hey, I want an F2 instance, essentially creates a container. So that's a software entity and basically isolates what runs on that container and is fully secure and in terms of cyber security and data integrity and data security, and it runs, and underneath it has actually the Xilinx FPGA, which the specs are available. But in this case, let's say F2 instance FPGA from AMD Xilinx is available to you, and essentially that there's a server. So just like when you have a PCIe slot in your PC or workstation, same idea applies. There's a CPU that's designated on the F instance, and via a PCIe bus, essentially it talks to the FPGA and downloads the image. And after that, that image has a fairly large bank of DDR4 that interacts with. Essentially, you download your design just like you would when you had the FPGA eval board on-prem and basically perform the same tasks. So, from a viewpoint of the developer, it looks exactly the same. So you could have an interactive F instance, created, which allows you, just like when you do, a Linux SSH to a node or a server where you're running your simulation. Same idea. So these two examples basically shows you a simulation being run and the waveform are being examined. So essentially, once you acquire an instance and download the image, those are lingo for the cloud, which basically creates you a container and fires up the application. The rest of the interaction is identical to having a Vivado, flow on your PC or workstation, or the Vidas, which is the C base. So you can take C models, and of course in here we are hardware centric view, RTL, and download to the FPGA and run it. And all that is without having any hardware whatsoever at your desk or on-prem. So again, the flow is this. Essentially, it's very simple. So basically, you get the encrypted design, and then S3 is our generic AWS storage. So basically, if you will, this is mimicking having a hard drive on your workstation. So you basically save the design on storage, and you just type this command one-liner, which basically says I want an instance of EC2, which is basically the family of instances, and what type of instance you want to create. You want to create an FPGA image. So that basically provisions an instance that has a FPGA on it, and this is a older slide. So in this case, this is F1 type instances, which is basically end of life. So now we do a F2 ingestion services that creates you the basically AFI, what we call, which is Amazon FPGA image. So now you have an instance that's fully secure and available to you. So upon executing the command, you get the instance created. So those were the steps at a high level, basically, for creating an FPGA instance. Now I want to focus on the engine we looked at up front, which was the smart of the flow to create, test benches, functional test suite for the design or device under design, DET. So basically, the generative AI application essentially is the product. So the iceberg example. So this is a generic AI ML type of application. So obviously you look at the output, or in our case, the functional test suite that's generated, but the majority of work is under the water level. So that includes the storage that you need and the governance and compliance. Obviously, you want to protect your IP and also the database. So all that test suite from, say, previous version, as well as the specification that's being parsed, all that is being stored in some database. And of course, there's data sanitization and so on, or integrating the data that you provide to the model. So all that information, it needs to be analyzed. So that's a huge amount of data. And the basic, what we're representing in here is, by doing it in the cloud, you're able to scale out, meaning that increase your memory storage and compute capability to achieve that machine learning result, which is that generative AI output that you use. And this is the value prop for a cloud offering. Otherwise, you would have to have a farm of CPUs, a huge amount of storage that, depending on how big of a database you need to have for your design, those are all complications that you need to plan for before the project, versus doing it in the cloud, which all is elastic and pretty much on demand. You can increase capability as you need to. And of course, looking at the different phases of a generative AI, basically, you get all this goodness available to you as well. So obviously, when you train a machine learning model, you need to feed it data, and then those needs to be analyzed, and who is running those data, and where are the data coming from different sources. So need to be all assembled together for a training AI engine job. And of course, because they're coming from different silos, they may not have the same quality of data. Then you have to analyze and basically sanitize the data that you feed. So all those capabilities are available in what we call a SageMaker, which is basically our AI ML offering from AWS. So you can basically perform all these tasks automatically by using a dashboard and the tools available to you. So yeah, I mean, so basically I mentioned that. So basically with the AI ML offering on the cloud, you're bringing a widely used training model and a comprehensive set of tools and different analytics available to you. So what are the advantages of doing it in SageMaker as opposed to individually? Of course, you can collaborate. So you could have a history of different projects that we have developed, in our case, functional test suites. And basically, you have one environment to control all your data. So say, in the example we talked about, if you are doing PCIe, say 5 or 6, implementation on FPGA, then you can basically get the data for the previous generations and have a repository that based on version, it includes or excludes a particular set of test suite. So that's the interesting part. As you know, when we respin designs based on different RAV, then when you find a bug, always the question is, well, was this a bug that was already there from previous version, or was it introduced because of the new capabilities on, say, PCIe 5 version? So in here, you can basically step through time and go back and forth and quickly resurrect the specific data set or test suite that you want to run against the design, and download the PCIe 4, say, implementation to FPGA, and then run that test suite. So you can basically pinpoint where was the bug introduced. Was it the previously version or the new version? And from that, you can take corrective action. Was the spec the culprit? So the specification is not correct, or was it that the test suite was not correct to catch this bug, or was there a bug that was waived and basically we accepted the risk to move forward? And as you know, a lot of cases when a new version of a spec is coming out, say it's PCIe 5, the development is a parallel. So we don't know if, the spec until it's ratified by IEEE or industrial consortium or whomever is running that spec. But as soon as it's ratified, folks want to have a version of that implementation so they can integrate and do plug and play testing and so on and so forth. So this gives you capability a lot faster because it allows you to step through and also find out where the gaps are. So even during development cycle or during ratification new spec, we can utilize our FPGA in the cloud with AI ML to help us pinpoint shortcomings and abnormal, let's say, behaviors to be analyzed. So, we have a few minutes left, so I'm just going to walk through some of these, and basically it's talking to the, data lake or a huge amount of data that you can look at, and also capabilities that have a, unified development from the AI ML side. And then, once we have the model developed, and in this case, we have the output from the suite of tests, we can utilize AWS Batch, which is basically an orchestrator. So what you do is basically you have what we call it job definition. So that's a template. And then each one of these jobs would be the single simulations we want to run from a slide we looked at. And all those jobs, you assign them, and they go into job queues. So you could have multiple queues depending on the type of job you want and priority and so on and so forth. And then once a job is fetched from the queue, basically a container is created, and then that goes to what we call a CE or compute environment. So that's the engine that actually executes the job, and the results are stored in S3 or a storage or a bucket in this example. So basically, AWS Batch is a fairly well-oiled machine, and it's been around for 8 years. And of course, we are really looking at the engineering type of applications, but it has a lot of different verticals that it plays to. And basically, the ECS is the virtualization that runs the simulation. It supports two types of services. One is EC2, which we talked to, so that's the F series. And then Fargate is another engine that you can run. It's a simulation based. Basically, it runs dirty and quick and dirty on simulations that are very short. So some of your power on reset tests, they could run on Fargate, and the advantage is it's less expensive. So you can choose. The bottom line is if you want to run your job on FPGA, or you want to do the traditional CPU simulation type of engine. And then we added the support for Kubernetes, and that's called EKS. So if you're familiar with Kubernetes containers, that's supported as well. So I know I kind of ran out of time, but this is all I had. So happy to answer any questions the team has.
We're out of time. Oh, sorry. We're out of time for the questions, so it's a break time here. So thank you for your talk.
All right, thanks so much. Have a great one.
Yeah, sorry to. So just going to finish with a quick thank you. See what's going up.
Mike, you would be sharing your closing slides?
Yes, we're doing it now. Okay.
Yes. Yeah, I can see. Please go ahead.
Yeah. So thank you for participating today. The presentations and slides will be available on the FPGA Frontrunner webpage there. You'll get an email on that. If you've got any ideas and suggestions for your preferred topics for future FPGA Runner events, just send them to me. We do have another one coming up quite soon on FPGA prototyping, which will be held at Rolls-Royce in the Midlands. And then we got our Verification Futures event. We have a new FPGA stream there. That's on July the 1st in Reading. Okay. You can see them there. So the one in Rolls-Royce is May the 21st, and that's been held with the ASIN, TechWorks ASIN for that's the automotive network. Okay. There's some DV club events coming up. One in a week's time on practical adoption of formal verification. And 19th of March is verifying automotive designs, and in Bristol on the 9th of April, AIML design verification. And we talked about verification futures. Okay, thank you to our speakers, sponsors, and our partners. So Venisure TestSolve and TechWorks, and the design network for TechWorks. And hopefully see you on May the 21st. Thank you.
Thank you. Thank you, Mike. Thank you, everyone. Thank you for joining.
I'm hoping that lunch will be outside. So for those of you that stay, then we've got about half.